Okay, good evening, everybody. Welcome to the joint meeting of the College of DuPage American Meteorological Society and the Chicago American Meteorological Society. I know we have a lot of students here today, so I just thought you should know we've got people from all over the Chicago area coming here tonight. We've got the cameras going on, so this will be streamed live. For those of you who need to check on some information, want to check it out again, you can go on our website. We'll have links to it. Tonight we're going to be talking about tornadoes, which is great. We've got summer weather for at least 10 days, I'm guessing. I don't see any cool down in any week and a half, 2 weeks. Hopefully all the way through June would be awesome. Today we have Karen Braun. Karen is a new part-time faculty here at the College of DuPage, recently coming from her master's that she received at the University of Oklahoma after getting her undergraduate degree from Cornell University. And she'll be talking tonight about some of the work that she's done on Vortex. Vortex is the verification of the origin of rotation within tornadoes experiment. And there was 2 parts of Vortex, which are huge scientific field studies to investigate tornadoes and the causes of tornadoes. And she'll be sharing a little bit later about her project, or her work on the project of Vortex later on. But first she'll be talking about work she did in her thesis, which deals with using a numerical model to investigate something known as a tornado cyclone. So we've got mesocyclones and we've got tornadoes, and we have something in between called the tornado cyclone. So I will introduce Karen and let her explain. Karen Braun.
Okay, so first we actually need to cut the lights, but not the back one.
Okay.
So just the front. Yeah. Okay, well thank you guys for coming out today. So first what I'm going to talk about today is some work that I did from my thesis from Oklahoma, and it was titled A Numerical Study of the Life Cycle of the Tornado Cyclone in a Simulated Supercell. That's a mouthful. So I will be going through that in a little more detail with you. But my advisor was Dr. Jerry Straka at Oklahoma. I did this work closely with him, and some of my committee members, maybe you recognize their names. Okay, so let's get started. So first I need to explain to you what a tornado cyclone is. Like Paul said, there is a 3rd scale of motion often neglected when looking at supercells. So very simply, a vortex is that vortex on the scale of motion between the mesocyclone and the tornado scale. So here's just some other terminology: parent circulation, vortex in which the tornado is embedded from the literature. Also, the literature has observed a maximum of 4 kilometers in diameter for this vortex. And also, it does not exceed what we call the thermodynamic speed limit. And the thermodynamic speed limit essentially relates maximum thunderstorm updraft speed to your convective available potential energy, or CAPE. So my CAPE for my simulation was about 2,200 joules per kilogram Kelvin, which would give you a maximum updraft speed of 66 meters per second. So luckily I observed my maximum updraft speed at 56 meters per second, so my vortex that I simulated did not break this speed limit. So I just wanted to point out the comparison of my simulation to real-life observations. So here I have a plot from my simulation. This is near the peak time. This is a radial velocity or meridional velocity plot, and it's kind of hard to see, but you have some storm relative northerlies shaded in the green, and you have some storm relative southerlies in the yellow, and our big arrows show mesocyclone scale motion, and the smaller arrows are the TC scale motion. So here you can see the mesocyclone is very well defined here. The tornado cyclone is very well defined, but you only see 2 scales of motion here on my plot. And I'd like to point out that this is a 12 by 12 kilometer plot that you are looking at. Over here is a WSR 88D radar image from a tornado outbreak day in Mississippi about 2 years ago. And similar to my simulation, you can see out here you have your mesocyclone. And here you have another scale of motion, and this is your tornado cyclone scale, but you can't see a third scale of motion from this radar image. However, if you look at the top image, and this is a Doppler on wheels radar image. So this is from a mobile Doppler that was able to get, I think it was about 2 miles from this tornado. So you can see here, maybe I'll use my laser pointer. So we have out here the mesocyclone, the tornado cyclone in here, and you see that third scale of motion right on the inside, and that's your tornado. And you're not going to see that on an 88D image, nor in my simulation, because my resolution or my horizontal grid spacing was 250 meters. I'll explain a little bit more what that is in just a minute. But I'm essentially not going to be able to resolve a tornado in my simulation. So why would I need to study a tornado cyclone, or why would anybody want to study a tornado cyclone rather than a tornado? Well, like I just said, the weather radars that we use can't resolve a tornado, but they can resolve a TC or a TVS, tornado vortex signature. They're like the same thing, essentially. And I've already showed you that mobile radars can resolve tornadoes, but we don't really use a lot of mobile radars. There's not a lot of them in the field. So most of our data that we can observe comes from that 88D radar. So tornadoes have a diameter of about 100 meters. So studies have suggested that you might need a horizontal resolution of as small as 10 meters to properly observe a tornado. And if you used a horizontal resolution of 10 meters, that would require incredible computing capacity, and it would take an incredible amount of time. So a lot of limitations with doing a resolution that small. So if you did try to simulate a tornado scale vortex, you would have very few observational studies to compare against, because we don't have a lot of cases of resolved tornadoes. So a tornado cyclone is appropriate to study in this case. So the purpose of my master's work was essentially to simulate this tornado cyclone, and I wanted to identify the key characteristics, both dynamic and kinematic characteristics, throughout its life cycle, so from the time it initiates to the time that it dissipates. And some of the things I investigated were vertical motion, so updrafts and downdrafts, pressure deficit, vorticity, maxima, amongst other things. And I really wanted to point out that these processes are most important at the low levels. So I'm defining low levels as 2 kilometers and below. And how I did this, I used my advisor's model, which was the Straka atmospheric model, a model that he wrote in Fortran himself. It's a 3D computer cloud model. And like I said before, my horizontal grid spacing was 250 meters. So if a tornado is 100 meters in diameter, 250 meter grid spacing is definitely not enough to properly capture that. So why would I want to focus on the low levels? So first, let me show you what I have here. Here I've taken XZ plots, so vertical cross-section, from my time of maximum intensity in my TC. And I have vertical vorticity plotted on the left and pressure deficit plotted on the right. I'll explain to you guys exactly what that means in just a minute, but I want you to notice here in the vertical, I used a vertically stretched coordinate. And what that means is that this model lets you see more levels at the lower level. So you can break it down smaller the lower that you go. And I wasn't so concerned about anything really above 3 kilometers, so my vertical resolution above 3 kilometers really didn't matter. But you can see here, I've drawn this dashed line at 2 kilometers. And you can see, here's my TC column right here. And this is 2 kilometers wide down here. You can see that most of my action is concentrated below 2 kilometers. So this just proves to me that I really do want to focus mostly on low-level processes. So I did a supplement simulation to mine using 40-meter grid spacing this time, as opposed to my 250. And I looked at the maximum time again, 8,220 seconds into the simulation, and I come across this. So you can see, here's my tornado cyclone, very well defined in both the zonal and the meridional wind fields. But now I have a third scale of motion being resolved right here with a diameter of about 200 meters. So that tells me that that is definitely my tornado. And what this also proves is that in my simulation, so if you go back here, some could argue that maybe that is a poorly resolved tornado. But this proves that it's not, because even if you decrease the grid spacing to 40 meters, the tornado cyclone is still very well independently formed. Okay? It's independent, it's there. So had I decreased my grid spacing, I would have definitely seen a tornado in my simulation. So I looked at a lot of past studies, both numerical studies, so simulations similar to the one that I did, as well as observational studies. And I based a lot of my focus on these past hypotheses. Do I want to support them, or do I want to refute them? So I'll be basing most of my conclusions off of past numerical studies and observational studies. So what set my study apart from other studies done in the past is, for one, I used surface friction for the entire simulation. Now, that's really important because obviously in the real world we have surface friction at play everywhere. So a lot of past models, due to time constraints, maybe whatever reason they don't use, it's easier to get a vortex in a simulation without using friction. Excuse me. And when you add friction, it just makes the simulation a little bit tougher. So a lot of past models have neglected friction. Some of them didn't completely neglect friction, but due to time constraints, again, only turned on friction at the start of the tornadic phase. So whether or not that's realistic, I don't know. Another thing that set my study apart is that I observed a really long-lasting cycle, almost an hour long. And that is kind of rare, especially in simulations, and especially in the field. People don't observe these things lasting for up to an hour. So with a 58-minute cycle, there's no way that I could share everything that I found in my simulation with you today. So I've broken it down really to 3 things that I'd like to share with you. And they all happen to be at the beginning, mostly, of this cycle. So I'd like to talk about the role of the rear flank downdraft in the initiation of the TC. I'd like to talk about the early development of both the pressure deficit and the cyclonic vertical vorticity near the surface. My vortex also went through a transition phase, which I'll explain to you what that is. And then finally, just so you don't wonder what happened for the rest of the cycle, I'll share with you briefly some of those things, but I'm not going to really focus on them too much. So I used thermodynamic profiles and wind profiles, both from Wiseman and Klemp. This is a past study that was done, a very widely used sounding and hodograph. And my sounding here gives me a constant CAPE of about 2,200 joules per kilogram Kelvin. And directional shear is very important, or has proven to be very important in the low levels when talking about severe weather. So I used a half-circle hodograph in the lowest 3 kilometers, and then above 3 kilometers, the velocities were essentially constant. So turning of the wind in the lowest 3 kilometers. So here is what my pressure deficit looked like for the duration of my cycle. So I've plotted the pressure deficit at both 2 kilometers and 80 meters for the whole duration of my cycle, and you see millibars here on the side. And what is the pressure deficit? So the pressure deficit is basically how much lower is the pressure inside that vortex than outside, so the ambient environment. Okay, because we all know that in tornadoes, in the center, the pressure is very, very low, right? So the pressure deficit essentially measures how much lower is that than what it should normally be with no tornado. So I've plotted this throughout the whole time. I have 5 different phases here, and I'm going to be focusing mostly on initiation and transition here in my talk today. I've also plotted vertical vorticity over the life cycle of the tornado cyclone, both at 2 kilometers and at 80 meters. And what is vertical vorticity? So vorticity is essentially a measure of the spin of the air. Okay? So the higher the vorticity, or the larger value of vorticity you have, the stronger vortex you're going to get. So you see that it looks a little bit messy here in the transition phase, and you have a very large spike at the surface in the dissipating stage. And that might be counterintuitive. You would say, why do you see such a large spike towards the end of the cycle? And I'll briefly share that with you at the end of my presentation. So first, I'd like to talk about the role of this rear flank downdraft in the initiation of my TC. So here I have plots from the very beginning of my cycle. So my cycle started at 6660, and here's 30 seconds later, both at 2 kilometers. All my plots here are going to be 5 kilometers by 5 kilometers. The top is the zonal winds, so the horizontal winds. And the W here is vertical motion. This black dot marks the center of the circulation, or the developing circulation, just for reference. And here I've shaded, on the top, I've shaded my storm relative westerly winds. So I put that yellow arrow in because it was kind of hard to see with the contrast of the projector. And then down here, with the vertical motion, I shaded my downdraft here in red. So you can see at the beginning of the cycle, you have a very strong region of westerly winds up here at 2 kilometers, which are co-located with a moderate size downdraft here. And here, in this 30 seconds, my westerlies increased by 2 meters per second. So these winds are increasing in speed, and my downdraft is also moving closer to the center of the circulation, along with this little patch of winds here. So here is the final 4 minutes of my initiation phase, and I'd like you to just focus on the top picture for now. Ignore this for right now. So 7140, this is the time when I decided that my TC had established. So I call this time TC establishment. So when I refer to that, that's what I'm talking about. So here's when my TC was officially established, and here's the 3 minutes leading up to that. Okay, so up here I've plotted vertical motion, and I've shaded, again, the downdraft in red, and then updraft in blue. And then I put these arrows just show the motion of the gust front. Okay, so here's my circulation up here, and then here's my rear flank downdraft wrapping around. So you can see that and then again, this is near the surface now, so this is 80 meters. So you can see, leading up to the establishment of my tornado cyclone, the RFD at the surface intensifies, and it wraps further and further into my tornado cyclone. So intensifying downdraft at the surface. So now I would like to look at this essentially advection. So here what I've plotted is the change in the zonal winds with height as a result of vertical motion. Now that might sound a little bit confusing to you, so let me try to explain it to you a little bit easier. So here, in purple, I have plotted the positive acceleration of this horizontal wind, of these horizontal winds as a result of vertical motion. So this downdraft is essentially intensifying these westerly winds that we saw back here, okay, that were brought down at the end of this cycle, or the end of this stage, to the surface, sorry. And you can see that not only are the winds accelerating, but the area of acceleration is increasing by a lot. So what does this tell me? That now Here's the same last 4 minutes leading up to the establishment of this tornado cyclone. Now here's the westerly winds, storm relative westerly winds at 80 meters, and you can see that now they're increasing and the couplet is strengthening as a result of the increase in these winds. So my first conclusion is that this rear flank downdraft transported the necessary momentum towards the surface to help initiate the tornado cyclone. And remember, in the last final minutes, so right here, this is when it was the most pronounced, right leading up to that establishment. And previous studies have also concluded the same thing through not always the same methods, but in the end, they all concluded the same thing. So now I'd like to show you how the pressure deficit and the vertical vorticity kind of intensified near the surface. So here what I've plotted, I've started at my very first time of 6660, and I've plotted XZ cross-sections of my storm. So here you can see these lines are the pressure deficit. Okay, so here is the mesocyclone. You can see it very clear, and the pressure deficit is about 8 millibars. And here's my developing tornado cyclone column. So this is the area that you want to focus on as I move through these images. And I've plotted them in 1 minute intervals so that we can really see closely how this pressure deficit is really developing. So you can see here, the mesocyclone has a much lower pressure than the tornado cyclone or the developing tornado cyclone aloft. But aloft in the tornado cyclone, the pressure is greater, or I'm sorry, is lower than it is at the surface. So the lowest pressure is here, then here, and then here. So as you move through time, the next minute, you can see that this little disturbance here intensifies. The pressure is certainly lowering, but it's still lower aloft than it is at the surface. So when you move through the next 3 minutes, you can see that our little area of interest, this pressure deficit is increasing, so the pressure is lowering over time. So now here is my final 3 minutes, and here is my TC establishment. So now you can see the last 3 minutes, it exploded. So I'm sure you possibly cannot see this. So I've blown this up. I've increased, or actually I've tripled the contour interval so that you can actually see them here. And so this is the final 90 seconds leading up to initiation. So you can see here, the pressure deficit is still greatest aloft, but it is pushing down towards the surface. Okay, so it's almost reaching the surface here. Now here you can see it's reached the surface, so there's almost 2 separate maximum, right here, and then the one up there. So that's, that corresponds to about 9.3 millibars. That's what that number means. And then here in the final minute, or I'm sorry, in the final time, the pressure at the surface is almost 10 millibars. The pressure deficit is almost 10 millibars. And aloft, it's about 9.6, right? So the pressure at the surface has lowered more so than the pressure aloft. So I will go over this conclusion in just a minute, but I suspect that this is as a result of friction. So let's look at the vertical vorticity. I've plotted the same time frame, the same cross sections here, and you can see here, here's my mesocyclone out here, and here's the column that I'm interested in for my tornado cyclone to develop. Now, this is likely a leftover from a previous cycle. This is, again, 6,660 seconds into the simulation. The simulation cycled. So there was other storms in my entire 2-hour simulation, but I just picked the one that had the best defined life cycle. So this is likely a residual from a previous storm. So I can't exactly say how that got there initially, but it's already there at the start of my simulation. So you can see that it is greater at the surface than aloft. There's not much going on aloft here. And you can see that by this time, 2 minutes into the life cycle, you start seeing 2 separate maxima there. So if I go to the next 3 minutes, you can see that this is definitely defined. Here's a maxima right here between 1 and 2 kilometers, and there's definitely one at the surface. And you can see that this is the case for all of these times. So what is this a result of? At the surface, this is a result of stretching of vorticity. And essentially what stretching of vorticity is literally the stretching of this vortex tube. So if you stretch it out, what are you going to do? You're going to increase that spin. You're going to increase that vorticity. So stretching at the surface is a very important process. But aloft, between 1 and 2 kilometers, this is a result of tilting of the vorticity. And what tilting of the vorticity is if you have horizontal streamwise vorticity, if you get any tilting, now you're going to tilt that vorticity into the vertical, and you're going to add to that vortex tube. So now you're just going to intensify the vortex tube. You're going to make it longer, essentially, in a nutshell. So tilting aloft and stretching at the surface are the two main processes going on here. So now in the final 3 minutes, here's establishment. You can see again, it kind of blows up towards the end. So I've plotted the final 90 seconds here, and you can see how much this vorticity intensifies at the surface, definitely more so than aloft. So I have the maximum vorticity, at least for the initiation phase, right here at the establishment. So what can I conclude from this? So the pressure deficit appeared to originate in the mesocyclone, and then it built downwards towards the surface. And then once it got to the surface, it intensified due to that surface friction that I had in place. However, the vertical vorticity appeared to intensify first in the upper levels, or I'm sorry, in the lower levels, and then extend upwards due to stretching. And stretching was more than double the magnitude of tilting. So stretching was really the dominant factor here to amplify my vorticity. So now I'd like to tell you about that transition stage that I observed. And I would like to tell you before we start that this was not intentional in my simulation. And actually, I almost missed it because it took about 4 minutes in my simulation. So if I had not looked more closely at that 4 minutes, I would have completely missed this, and I would have never known that this happened. So it's really interesting. So I want you to recall, this is my plot, or this is my graph of vertical vorticity over the entire simulation, or the cycle, sorry. Here's my transition phase, okay? So something strange is going on with that vorticity. So what I did is I broke it up into a new vortex, an old vortex, which is the blue. This is the original vortex that I observed. And then a new vortex that happened to form during this phase. And so now I plotted the vorticity over the entire simulation again at 80 meters and at 2 kilometers. And you can see that here, so now I've highlighted where my transition phase is. You can see at 80 meters, here's the original vortex. And then somewhere right here, a new vortex starts forming. Okay, and so eventually that old vortex died out and the new vortex became the dominant vortex throughout the entire simulation. But at 2 kilometers, here's your original vortex, and then the same thing happens. A new vortex comes along, weakens that old vortex considerably, but eventually it prevails and it continues on. So why would that happen? So here, I broke it down even further. Now I've plotted it at 80 meters, 1 kilometer, 2 kilometers, and 3 kilometers. And I noticed that here, at 80 meters and 1 kilometer, you can see that the old or the new vortex eventually takes over the old vortex. But now here at 2 kilometers, this new vortex weakens this old vortex, but the old vortex does still prevail and continue on. You can see that at 3 kilometers, this is much less pronounced than at 2 kilometers. So I went back and I investigated, and I found that the cutoff was about 1.8 kilometers. So below 1.8 kilometers, it was a situation like this. the new vortex took over and the old one eventually died out. But above 1.8 kilometers, this the old vortex was weakened, but it still ended up prevailing in the end. So here's actually a 4-minute span of my transition phase, and this is at 80 meters. So these are 5 by 5 plots of vertical vorticity. And I want you to look here. So here is my original vortex. It's very strong. You can see the vorticity is very strong. But over here, here's my new vortex forming a little vorticity center that's quite weak. But you can see with time, it is intensifying, but is intensifying separately from this original vortex. Okay, so they're intensifying and weakening independently of one another. So eventually, this new vortex becomes stronger and becomes the dominant vortex, and this one, the original one, essentially died out. So this is what happened at 80 meters. Now if we look at the same exact thing at 2 kilometers, you can see here. Here is my original vortex. It's very strong, but you can see over here, here's a little disturbance. So here's that vorticity, and it's intensifying. Okay, but it's still not stronger than the original, and it actually never becomes stronger than the original. In fact, it almost looks like this original vortex almost sucks in this vorticity center, and it becomes one by the end. So you can see it almost travels around, and then into that center. So you can see that the old vortex pretty much ends up prevailing at 2 kilometers. So I figured that the vertical velocity had to have something to do with this. Why would the low-level vortex die out, but above 2 kilometers, it doesn't? So I looked at vertical motion at 80 meters just prior to the start of this transition phase. So the transition phase really starts right here. So again, I have plotted here, the red is the downdraft, and the blue is the updraft, and this black dot is the center of my circulation. So you can see that this rear flank downdraft comes in and fully surrounds this updraft, essentially cutting off that warm air, okay, cutting it off, cutting that updraft off, and essentially that kills the vortex. But you can see out here in front, there is an area of new updraft, and this green is the new updraft area. Okay, so here it is over here, and it is located in the same place as that other vorticity maxima that I showed you before. So here, the same time, here it is out here, and now here is my updraft center located right on top of that vorticity center. So great location. But at 2 kilometers, this does not happen. You can see here, I've shaded the updraft in blue, again, in the downdraft in red. Maybe the updraft weakens a little bit, but nothing like we're seeing here at 80 meters with a full surrounding of the updraft by this downdraft. So what can I conclude here? So my rear flank downdraft ultimately contributed to the demise of that original vortex. So what did the RFD do? It essentially choked off that updraft at low levels. But while the RFD weakened that updraft at 2 kilometers, the original updraft eventually prevailed, and it was able to strengthen again after this little transition phase. But remember, I had that new updraft located right by that vorticity, or right on top of that vorticity maximum. So that was able to facilitate a lot of stretching of that vorticity, and that vorticity amplified really quickly, as you saw that new vorticity amplified very quickly. And again, below 1.8 kilometers, this new vortex eventually prevailed. Now I do have a really cool case study that I saw when doing my thesis. I found that essentially this happened in real life. So March 13th, I guess exactly 22 years ago, this happened in Heston, Kansas. So what happened, this is the actual observations from that tornado. You had one tornado that was originally an F5 tornado, well, at one point it was, it comes here, and essentially it dies out. But before it dies out, a new tornado forms and strengthens as the original one weakens. So if I look kind of midway through my transition phase towards the end, here's at 80 meters in my simulation, you can see that the position of this new vorticity center here is very similar to the location here. You can see that it's like almost on a diagonal, right? And so here, this new vorticity center intensifies here, and you can see that this original vortex almost seems to come around the back, kind of like this did here. Okay, do you guys see that? Mm-hmm. Very, very eerily similar, I thought. And here's a picture of this occurrence, and this is about 3 minutes into the transition. So you can see, here's the original tornado, it's dying out, but over here, this tornado is intensifying very, very quickly. So very, very cool to see that something that happened in my simulation actually happened in real life. And when I looked at the moisture and the winds, the wind profile was very, very similar. The moisture profile was almost exact. The CAPE was very similar. So very, very similar real life case. So finally, I just wanted to talk about really briefly what happened throughout the rest of the cycle. So in my intensification and weakening phases, this is right post-peak, or pre-peak, and post-peak. I have an occlusion downdraft that shows up about 7 minutes after this transition phase. And I observed that this downdraft was warm. It weakened the circulation a little bit, but not too much, and it eventually went away. Then, 7 minutes later, I see my maximum intensity reached, but at the same time, interestingly enough, a new, actually anticyclonic circulation starts to form about 8 kilometers west of my tornado cyclone, and this comes into play later on in my dissipation phase. So the rear flank downdraft and this occlusion downdraft that kept coming and going, they were very, very, very random with their behavior. They were both strengthening, weakening in almost random fashion. In the RFD, I generally observed that it was a cool downdraft, and the occlusion downdraft was a warm downdraft. And that's what you normally would expect. But I did actually see bursts of warm RFD and cool occlusion downdraft. So definitely a little bit different. So here I am at my maximum intensity. This is at 80 meters here at the top. And this is at 2 kilometers here at the bottom. So my zonal winds over here, and my meridional winds over here. So you can see a very nice tight couplet there. And here I've plotted, or I've graphed, or charted, whatever you want to call it, some of the maximum intensities that I saw. So my pressure deficit and my vorticity was the greatest at 80 meters. And so were my winds. They were the greatest also near the surface at just about 40 meters per second, a little bit more than 40 meters per second. But of course, as I would expect, my updraft at 2 kilometers was a lot greater than at the surface. But for the most part, the surface was the most intense that I observed. So as my tornado cyclone dissipated, I saw that the pressure actually was decreasing at the surface, but not so much aloft. So now this results in a large upwards pressure gradient force. So what happened? A new updraft actually formed at the surface because of this. So you had divergent air coming from the RFD, and this formed, or this met with that gust front. And now this air was forced upwards, up and over the sinking air. Okay, so now this is going to be intensified by this pressure gradient that I mentioned before. So this is at the very lowest levels that this is happening. So an updraft surge in the low levels is going to intensify that low-level tornado cyclone. So remember when I showed you that full graph of my vertical vorticity, you had that really large spike at 80 meters at the end. And so this explains why you saw that. And it appeared that my tornado cyclone actually dissipated. From the top down, you had the variables were very unbalanced. They were kind of all over the place. But that other anticyclonic circulation, it actually formed a new anticyclonic tornado cyclone that had really taken over and really taken away attention from my tornado cyclone. And of course, the RFD and the occlusion downdraft eventually dominated the column, and my tornado cyclone died out. So, in conclusion, overall, I saw that to initiate my tornado cyclone, I needed the rear flank downdraft to bring that momentum from 2 kilometers down towards the surface to get things going. Also, I observed that my pressure deficit originated in the mesocyclone and extended downwards, while my vorticity intensified at the surface and built upwards. Also, I saw that a low-level vortex actually formed during my transition phase, and below 1.8 kilometers, this new vortex essentially became the main focus of my cycle. And of course, friction really played a big role in my simulation because it determined the behavior of my pressure and my vorticity, especially near the surface, throughout my entire cycle. So, I guess that's it for my research portion. So, are there any questions about this, or should I not do questions yet?
Do questions after the
Okay. So now I'm going to talk a little bit about my time on Vortex II. Okay, so Vortex II was a project that lasted over 2 years, about 5 or 6 weeks in each year, 2009 and 2010. And as Paul said, this was the verification of the origins of rotation in tornadoes experiments, and we shortened that to Vortex. So there was a Vortex I, and that happened in 1994 and 1995. They had about 18 vehicles back then, and actually Vortex I inspired the movie Twister, which came out, I think, in 1996. So it was actually inspirational to that movie. The second phase of Vortex, Vortex II, was in 2009 and 2010, and this time we had about 50 vehicles and about 120 participants. We also had $12 million from the government that really helped out, and we drove about 20,000 miles per vehicle combining the 2 years. So my van drove about 20,000 miles over the 2 years. So there were a couple main goals of Vortex II, but the primary goal was how, why, when would tornadoes form, and why are some very strong, why are some weak, and also why do some supercells spawn tornadoes and some do not. So the null cases were also very important in our research. We want to know more about the structure of the tornadoes, so the wind speeds are important, the damage is very important. And how can we forecast tornadoes better? How can we improve that lead time of about 13 minutes to possibly even an hour? Is that possible? Well, we don't know. But that is the goal, to try to see how or if we could do that. So we were led by 8 very smart, bright people. This is our steering committee, very experienced in severe weather research. And we also had about 20 to 25 project investigators, so PIs, and they led each individual team. So these were the main bosses, and then you had your PIs, and then you had you know, the rest of the people. So we had quite a bit of vehicles, quite a vast array of different instruments. So we had about 10 radar trucks, and here's one of the radar trucks we had. They were different beams, all different types of radars. This is just one of them. We had 12 mobile mesonets. These are the mobile mesonets. They were vans with a big instrument package on the top. So they could measure things such as wind speed, wind direction, temperature, humidity, all sorts of things. We had 14 tornado pods, and this is a tornado pod. So essentially what they would do is they would take this big heavy thing, I think it weighed about 120 pounds maybe, so two people would carry it out in front of the tornado and essentially put it down in front of the tornado and hopefully escape. So that was the goal of the tornado pod. And then you had 4 disdrometers, and you had, let's see, oh yeah, the stick nets. They're kind of similar to the tornado pods and the mesonets, but it was just the way that the stick nets were set up that made them different from the mesonets. And I'll show you where all these instruments essentially went within the storm. But we had 5 photogrammetry teams, and I was actually part of that, and I'll explain to you what exactly we did. But we had scout vehicles in order to tell the radars, okay, can you clear this bridge? Can you park here? And things of that nature. We had a field command vehicle, so we had one person, the steering committee, sitting in there. It's an ambulance, essentially, looking at all the stuff, telling everyone where to go, making the decisions. And we had teams out there launching weather balloons at appropriate times. So here is a group shot from 2009. So you can see all the different types of radar trucks here. Here we have a mobile mesonet. Here's some stick nets, tornado pods. And here's the field command vehicle. So it actually was an old ambulance converted into a essentially a mobile laboratory. So I was part of the photogrammetry team. And here's our equipment. We had a digital camera set on a little platform. And we had GPS devices on top of the camera, as well as at a distance from our camera. And what we wanted to do was take pictures at 5-second intervals. Okay? And what we wanted to do was capture storm scale structure. So we were looking for things such as the inflow notch, updraft base, things of that nature. And so what we want to eventually do is take our pictures. This is not one of our pictures. This is from another photogrammetry team. But we want to be able to take our pictures and then, based on our GPS data, take radar data from the radar trucks that collected that data and overlay data such as you see here. So here we have the winds with the blue arrows and the reflectivity with the red contours. So this is the eventual goal of our team's project. So here's the domain of Vortex II, pretty much concentrated in the central plains here. You can't really go west of Oklahoma City, like into Arkansas, because there's too many trees, too many hills. That is not conducive to chasing. You can't really go into the mountains, also not conducive to chasing. And of course, if you get too far south or too far north, you're not going to really see severe weather too much at this time of year. So this was our optimal domain. And here's what a typical setup would look like. So here you have your supercell. Here's a supercell hook. So here you have all your stick nets kind of sampling the entirety of the storm. You have your mobile mesonets running transects through the storms. You have radar trucks set up at various different locations here. You have the photogrammetry teams set up. You have balloon teams set up. Okay, so this was the ideal deployment for our project. So here's a typical day. Here's just one of our days from 2010, actually June 2nd. And that day we started in Hays, Kansas, and we drove to western Kansas up here. We drove around for a while trying to do our deployments. Actually, my van got stuck in the mud that day. It was really sad, but we eventually got out due to the great driving skills of one of our team members, and we headed to Valentine, Nebraska that night to position for the next day. So this is just a typical day on Vortex II. So what did the actual day look like? What did we do? So this is just an average day. So at 8:30, the steering committee gets together and says, okay, where do we think things are going to happen today? What should our overall plan be for today? And then at 9 a.m., the PIs come in with the steering committee and they all decide on a grand operation plans. So about 10 o'clock, everyone comes in and one of the PIs gives a weather briefing to all the members, and we're given essentially a target and at what time do you have to be at that target. Now the target is not necessarily where the storms are going to form, but the target is where do we want to position ourselves to then wait for that next step, because it's very hard to know exactly where those supercells are going to form early in the morning. So we had to, a lot of times, go someplace, wait, go someplace and wait. So let's say around 2 p.m. maybe you arrive at this target and you're waiting again. A lot of waiting around happened, but you know, that's just kind of the nature of chasing. So we would relocate if we were told to. You know, we're essentially just waiting for convection, waiting for those storms to basically begin. At some point you had to eat, so eating a lot of times was a problem. A lot of times we go to Subway and get a foot long and eat one half for lunch, and then if we don't get dinner, you got to save the second half, because sometimes you didn't get to the hotel till like 1 a.m. In the case of the Valentine's Day, Valentine, Nebraska, that was the case that night. So you wanted to always have an extra stash of food with you just in case. So typically between 5 and 9, that's when we saw the best supercells. So we were deploying, or at least trying to deploy. Sometimes things didn't exactly work out, so we didn't really get deployments every single day. But we would continually update our targets as we would go along. New targets would form nearby, so we'd go to those. And we all had radar on a laptop in our vehicles, as well as a communication system where we could see every team's position relative to the storm. So it was really useful. We had a lot of communication between the vehicles. And then, if you're lucky, maybe 9 p.m., you can maybe head towards the hotel, which is decided at some point during the day. They'll decide where you're going to be spending the night. And, of course, you're going to hope that you're not driving 300 miles to get to your hotel after your long day. And that was sometimes an issue, but we dealt with it. So there's some limitations that were involved in Vortex II. And there were some particular storms that Vortex II missed, but there are reasons for why this happened. So your first limitation is you had a lot of vehicles, you had a lot of participants. Okay, so you really have to think of the best interest. You have to think in the best interest of a group of 120 people. Okay, so driving all night, you know, like a madman to get to a new target, really isn't in the best interest of a group that's on the road for a month at a time. That's just going to wear you down. Okay, so also, if you have a lot of fast-moving storms, this can be very dangerous to a large group, and people aren't going to be able to reposition in time. You can possibly put these teams in danger. So you have to consider those factors. Again, kind of jokingly, but not really jokingly, you are operating on government funds. So we were told to obey the speed limit. Of course, you should obey the speed limit at all times, but especially for us, you know, some of us were operating, you know, multi-million-dollar equipment on our vehicles. So really obeying the speed limit was really more of a you know, safety for our equipment, not necessarily us. But so you know, we weren't able to, you know, drive at 100 miles per hour to get to this new target. You know, that was not feasible to do. You also need a sufficient and safe road network. Okay, so dirt roads for us are not safe. You cannot get a humongous radar truck stuck in the mud. That's a terrible idea. So where there's not a lot of roads, like for example, Cherry County, Nebraska. Okay, there's not a lot of roads there. So chasing in Cherry County is nearly impossible for a group like Vortex II. So we're looking for paved roads and a very good road network. Also, you have to consider your long-term positioning. So you have to think, okay, well, we're chasing this marginal target today. Is this going to put us significantly out of position for a very good target for tomorrow? So that was also taken into consideration. We didn't want to move a whole crowd of 120 people too far out of position. Also, those down days are actually necessary because we have vehicle maintenance that needs to happen, oil changes, because you are driving these cars up to 700 miles per day every day. So you do need to take into consideration maintenance, windshield replacement. That happened a lot. things like that. And also laundry. Okay, how can you possibly pack for 6 weeks on the road in a small suitcase? So laundry was needed to be done, and of course resting. I mean, we need rest sometimes. Going for a month at a time can be quite tiresome. So definitely some limitations involved with a project of this size. So during my downtime, I got to do a couple cool things. I hiked the Badlands in South Dakota. I went to Mount Rushmore. I went to the Twister Museum. I got to hang out in the Tornado Intercept vehicle from Storm Chasers. So we actually got to do a lot of cool things. Some people went to a Rockies game in Denver. So it was definitely a good experience. You got to see a lot of things that you likely wouldn't. So the downtime was also fun. So I just want to show you a couple of my pictures. And I actually have a video of our deployments that I can show you in just a couple minutes. But here is the famous Vortex Tornado. This is the Goshen County, Wyoming tornado of June 5th, 2009. It was an EF2, and it was the most heavily sampled storm in history. So we made history this day with this tornado. This was after 4 long, very frustrating weeks of essentially nothing. So, well, null cases. So we didn't see any tornadoes. We were all very tired and frustrated. So when we saw this, this was just like really like the greatest moment ever. So, so here was the meso pre-tornado. So here it formed. I was very excited. This was my first tornado I had ever seen, and what a great one to be the first. So here you can see it's about to be rain-wrapped, and it was rain-wrapped for a minute or so, but then it emerged again on the other side, and it eventually roped out at the end of its cycle. So that was a really, really cool tornado to witness. As a result of that, one of our mobile mesonets actually received softball-sized hail, so 4.5-inch hail to this vehicle. You can see this dent here. It's very hard to see, but I mean a really humongous dent in this vehicle. And this windshield is actually being held up partially by these Mountain Dew bottles, believe it or not. So this person had to drive back to our base that night looking out the window, essentially, because that's how bad it was. And of course, this windshield was replaced the next day, but you did have, no windshield was broken this much, no other one. But of course, even if you have a little crack, if you're out in the field the next day, you get a little bit of hail, that could blow it in your face. So that's dangerous. Any crack, you have to get repaired. So that was happening a lot on our trip. A couple days later, we saw really huge hail in Missouri, and this was actually about 10 or 15 minutes after the fact. So originally, these were probably about tennis ball size. So really cool to see that in person. You don't see hail like that every day. Here was a little vortex that I took while the van was moving. So I was in the back trying to like snap all these pictures because we were trying to position ourselves to another target. But I saw this little funnel coming down, and it was really cool because you can see, okay, it might be on the ground there, maybe here. I can't tell for sure, but as it dissipated, a new little vortex kind of formed to the side. So the real interesting thing to happen, watch happen, and this happened in a span of probably about 90 seconds. So really, really cool. We also didn't always see tornadoes. Obviously, we didn't see tornadoes very often at all. So you saw a lot of cool structures. So a high precipitation supercell up here. Nice little rainbow out here in New Mexico. So really cool things other than tornadoes.
There's a lot of tornadoes the day after you guys quit.
Yeah, thanks for telling me. Okay, so I'd actually like to show you a video of our deployment. And this is from our team, and this is about a 5-minute video. Okay, so not all these deployments are the best, but you can see here we're setting up our little GPS here, and we have to reposition obviously sometimes. But what we're doing here, you can see that somebody is out there holding a hose with water in it. I don't know if you can see Yeah, so you can see the person is kind of moving from side to side with this hose. And essentially what that was a very, very like old school way of verifying our angle, so our pitch and our roll on the camera. Because in case that failed, we wanted to have backup. So that was a way that we could verify by looking where the horizon is in the camera. So I know the Goshen tornado is coming up at some point here. So not all these deployments are necessarily usable with the radar data, but we do have two teams positioned about, I think about 7 kilometers or 10 kilometers apart for the purpose of getting 2 different angles. So I think Goshen is actually coming up fairly soon.
You guys encounter a lot of lightning on these cases?
Yeah, here's Goshen. Never really that it was dangerous to us. It was more after the fact, like when we're driving home. That's when the lightning was really intense. So it never really was a danger too much. Yeah, so there's Goshen from another perspective. You can see it gets rain wrapped, but then I think you can see it. Oh, I guess no. So a lot of the times we wanted to position ourselves so that we could film the back of the supercell, because that's where we can see, a lot of times you can see the updraft face very well. And this is really what we wanted to capture, the inflow notch, those sorts of things. So really nice mammatus clouds there in that shot. I think there was only one time that, that we felt a little bit unsafe during the deployment. There was one time where a funnel essentially started to form over our head, and we were so freaked out that we threw everything in the car and we actually left our hose in the field. So we were driving along like, oh, where's our hose? Oh, it's in that field. So we had to go back and retrieve that. So that was really the only time where we were like, oh my God, like we could be in danger. So most of the time we felt pretty safe. Really didn't feel that we were in too much danger, because we did trust the people that were leading us, telling us where to go. We trust that they're not going to put us in harm's way. Let's see.
Is that a government issued hose or?
Yeah, you would think. Let's see. Okay. So this was actually an anticyclonic supercell. Really, really cool. And I don't think this could possibly be all of the deployments that we had, but this is just, I guess, some of the best ones that we had. And all of them are very different, as you can see. Okay, I think that's all for the video. Okay, so that was essentially Vortex in a nutshell. and my master's work in a nutshell. So I guess if there's any questions.
So we have time for a couple questions if anybody has some for Karen. Evan's going to walk around with the mic so we can get you on.
Yeah, very well done. I really enjoyed it. Two questions.
Thanks. Mm-hmm.
In the first part, you mentioned that extreme stretching for vorticity tube. What was causing that?
What was causing that? Really, it was the friction at the surface that causes that. It really amplifies the stretching. So in non-friction simulations, you won't see stretching as intensely as you would with a simulation with friction. So really, friction is the factor in amplifying that.
Okay, and then I heard also when you had that deployment, you guys were really trying to keep your locations quiet so you wouldn't have additional chasers going after you. Was that successful or not?
Right. Well, actually, yes, because a lot of the times we were kind of in locations where there weren't a lot of chasers. Some days we actually did encounter, we were chasing near, I think it was around, I can't remember, maybe like Perry, Oklahoma, Woodward, in that area. And there was just so many chasers out there that we could not get in position. So we tried to keep our locations quiet so that people would not try to come out there and see what we were doing, disrupt our operation, because we did have to a lot of times pack up quickly and move and be able to get there. So if they're clogging the roads and we can't really position, and all of that, those great resources and all that money kind of goes to waste. So we really wanted to take full advantage of our opportunity.
Were you successful with that in keeping it quiet?
Yes, for the most part, yeah. I mean, we asked people, on the project to not tell your friends where we're chasing, to not, tell people where we're planning to go. So, yeah, for the most part, that was pretty successful. But sometimes you just can't avoid that. Some locations are just more heavily, clogged with chasers than others. So. Mm-hmm.
Yeah, I wanted to ask you about your modeling. Do you feel that your model verified what occurs in nature, or that was the other way around, that you observed something in nature and your model was good?
So are you asking if when something was observed in nature, the model was built around that? Or are you saying?
Well, yeah. Did you try to verify the model with nature, or did you try to model nature?
Well, like I said, I didn't write the model. My advisor wrote the model, and he's actually been writing it for the past 30 to 35 years. So it's kind of an ongoing, an ever-improving model. But really, he tries to formulate the model to where it will most realistically simulate the real world. So it uses really advanced microphysics, so you can simulate all types of different precipitation, so just to make it as realistic as possible. So when you do see stuff in the simulation, like I saw with that Heston case, then you can see, okay, well, our model probably is, you can probably compare that to what's going on in nature.
So you're really verifying the model against nature?
Essentially, yeah, and then improvements can be made to the model, and he's been improving it continuously for the past 30 years.
And then one other thing, specifically about the Heston, even more ancient history than that was the super outbreak in April 3rd and 4th. That was the first time a lot of those families were identified after the fact from aerial photographs.
Right.
And this seems to be the same type of thing. So back then there wasn't the computing power or the models to simulate that kind of thing. So this may be, if you went back farther, you may be able to find other cases.
Oh, definitely, yeah. I'm sure that I would be able to, but like you said, yeah, there just wasn't as good observations back then. There wasn't models to, verify those kinds of things.
Well, there weren't the observations either. No one had cameras then.
Oh, yeah, exactly, yeah. Yeah. Yes, we're here.
If you have a stretching vortex, it's getting narrower. Does that also mean that you have an increasing pressure gradient?
Actually, yes. The vorticity and the the vorticity and the pressure deficit, at least, they change together. So essentially, yes, you're going to get a larger pressure gradient. So it's not really known really what happens first. It's kind of a chicken and egg sort of thing. Like, does the vorticity reduce the pressure? Does the pressure reduce the vorticity? I mean, it's very, very hard to pinpoint. So, but they do definitely change together.
Okay.
For the most part.
Maybe one more question, Chris?
Okay, I was just gonna ask, while
Wait.
on, a little easier. On Vortex 2, during the analysis process, how many of you actually did like a map analysis or did modeling? Like, how could you maybe describe a little bit of the analysis process when you guys decided to go to a certain place, or when you thought severe storms would form in a particular area?
So really, it was up to, like I said, like the steering committee and the project investigators, really, who would get up in the morning. They'd look at the models. I mean, the same things that chasers do. I mean, really similar things. Look at the models and see, okay, where's our best chance, and then position ourselves kind of at least within that area so that we can then change locations. We don't want to commit too hard to one location. We want to keep our options sort of open, especially earlier in the day, because as the day goes on, that target can change. So really the same things that anyone would look at for the most part.
Was there a map analysis you guys did in the morning?
Like a hand analysis?
Yeah, like hand analysis.
No, I mean, no, we really didn't have time for that, unfortunately. But no, I mean, these people that were leading the project can almost essentially do like a hand analysis in their heads, if that makes sense. Like, they can just look at it and say, okay, like, I get this, I see what's happening. So luckily we had really talented people that really knew what they were doing. And they really, even though 2009 was like one of the lowest tornado years ever, we were on the supercell of the day, the storm of the day, every day. So I mean, and we're chasing C-text, okay? We're not even chasing slights here. So I mean, to be on the supercell of the day with no outlook really, I think that's pretty impressive. And those people did a really, really good job. So.
Okay, thank you, Karen.
Yes, thank you. Thanks.
Just want to make a few announcements here. Sam, we were talking about the Skilling Severe Weather Seminar.
Saturday, April 14th.
Saturday, April 14th. So anybody who's interested in Fermilab, Tom Skilling has done this for, gosh, 400 years, I think. And then Chicago AMS.
We have our annual banquet coming up on April 28th. We'll be at the Bohemian Garden again. Cost is going to be $30 this year. And we have one of the U.S. Air Force Reserve hurricane hunters coming to talk to us.
That'll be great. It's going to be during our Chase 1, so I encourage other ones. And the Bohemian Garden is wonderful Bohemian food. So we have some soft drinks and cookies if you would like, and to talk to other people or ask Karen questions. If anyone's interested more in storm chasing, come talk to me about it, and we can actually go out there. But I'd like to thank all of you for coming tonight and wish you the very best.